We'll continue this discussion. We are into this module 5, where we are discussing this behavior and design under Flexure. So far, we have been discussing only the moment curvature behavior, and we are looking at different parameters. We looked at what is the effect of increasing the steel for a singly reinforced section on the tension side. For an under reinforced section, we looked at what is the effect of concrete strength, increasing concrete strength on the moment curvature behavior. In the last module, we also talked about what is the effect of axial compression, okay, on the moment curvature behavior. So we'll continue the discussion. And now in this module, we're going to talk about what is the effect of compression reinforcement on the moment curvature analysis, right? So what are the expected learning outcomes? The student should be able to derive or draw the moment curvature curves for RC sections which are also having compression reinforcement, that is the reinforcement on the compression side, and should be able to discuss the effect of compression reinforcement on the moment curvature behavior of RC sections, and explain the reasons for providing compression steel, why, when, in which scenario that you are going to put compression steel, and should be also able to explain the relationship between moment curvature and load deflection behavior. So these are the expected learning outcomes after the student sees this video, right? So most of the times you would have seen that beams will have steel on the compression side as well as on the tension side. Okay, the reason is for various architectural requirements also, the size of the beams will be limited. Again, we have studied in the first part of the module, the cost of the formwork in concrete cast in place construction is quite high. So to optimize the cost of construction, we try to keep as much as possible the size of the beams to be nearly same, and we'll group them, okay, depending upon the load requirements and so on. Not deviate the size of the beams too much, as much as possible, right? So again, for loading point of view, if your size of the section is limited, then singly reinforced section, we cannot keep on increasing steel and get more moment resistance. We have seen that when the steel becomes more than balanced reinforcement ratio, then you don't get much moment capacity, right? So that is another reason. One reasons we have to also put steel on the compression side to get more moment capacity. Sometimes we also want to reduce the level of stress in the concrete on the compression side and relieve the concrete from taking more stress and transfer the load to the compression steel. So that reason, from service level stress analysis point of view, sometimes we would want to put steel on the compression side. More importantly, putting steel on the compression side is going to help in reducing the creep of concrete. We've talked about what is creep of concrete, right? So under constant stress, concrete and compression will, the strain will keep on increasing over a long period of time. Okay, so we talked about basic creep, secondary creep, and so on, drying creep, and so on, right? And the effect of creep can be quite significant sometimes. Okay, and that is going to increase your long-term deflection. So to reduce the creep, one way is to also put more compression steel. And again, as we've said, sometimes we want to reduce the stress in the concrete in compression, and we want to reduce the sustained load deflection, which we will discuss in the coming slides. And also, some level of compression steel is required to hold your stirrups while you make the reinforcing cage for a beam. Okay, so that for that purpose also, and from ductility point of view also, we add compression steel. Now let's see. In fact, in 1952, Washa and Fluck, they have done some testing. Okay, so it's almost 70 years ago, right? They have taken RC sections and then they looked at three scenarios. Okay, and here the rho prime is nothing but your compression steel. Okay, compression steel. Okay. Now rho indicates tension steel. Rho prime indicates compression steel. So they looked at three cases. One beam with only tension steel, okay. Another beam with with a compression steel of about 50% of what we put in the tension side. Then the third case was beam with similar amount of compression and tension steel. So what they did is they took a simply supported beam and they applied some load and they kept the load constant, and then they went and checked the deflection, how the deflection is changing over a period of time. So that's what we are plotting here. We are plotting this midspan deflection on the y-axis, okay, and on the x-axis we are measuring time. Okay, so let's say I start loading from day, I consider that day as 0 day, and then I'm measuring the deflection for let's say every 10 days or so, and they measure the deflection for almost up to 2 years. So what you see here is as soon as I start applying the load, of course, I'm going to have some deflection. So that is your initial deflection. Okay, that is this. So roughly it is about 50 mm deflection. Now, when the load is remaining constant, your deflection also should remain constant. That's what you would have studied in your structural analysis, right? When the system becomes elastic and the load is applied, you get some deflection. And if I'm not increasing the load, the deflection should not ideally increase. But however, it doesn't happen because of the sustained effect of concrete undergoing creep. And concrete also undergoes shrinkage. Because of creep and shrinkage, you will have additional curvature that are happening to the cross sections along the length of the member. That is going to keep on increasing your deflection. So that's what they said. They looked at the three cases. So if you see that blue color is the beam which is a singly reinforced section with only steel on the tension side. You see, even though my initial deflection is 50, the deflection start kept on increasing, and it went almost as high as 150 millimeter. So short-term deflection is the one that you measure right after the application of loads. It's 50, but at the end of 2 years, the deflection has increased to 150 millimeters. So how many times that it has increased? It has almost increased 3 times the total deflection. So you can see here the effect of sustained load or the creep induced deflection is almost 100 mm compared to the short-term deflections of 50 mm. So that is why you must have studied in your creep coefficient. We talked about it in the material aspects also. Creep coefficient, if you look at, we reduce elastic modulus. Elastic modulus is reduced by short-term modulus divided by 1 plus phi. Phi is your creep coefficient, and the maximum value in the code is given as 2.2. This is the reason. So if your elastic modulus is reducing by 1/3, your deflections are going to increase by 3 times. So that is exactly what it is also happening in the experiment that is done by Washa and Flood. But I can reduce this effect of your creep by putting compression steel. So they have seen that if I am putting 50% of compression steel for the same beam, now the deflection, the sustained deflection has reduced from 150 to roughly about 100. If I'm putting the same amount of compression steel, now if you see here, the deflection has become only about 75 or so. So 75, this is 100, and this is 150. Okay. So you see here, by putting compression steel, we can substantially reduce the effect of your sustained deflection. So, and that is because the compression steel is relieving the stress in the concrete. And when the concrete is subjected to less level of stress, it's going to creep less. So, and it is going to lead to a lesser sustained deflection. Okay, so this is the thing. So by adding compression steel, it is going to reduce the neutral axis depth. So when you have reduced neutral axis depth, how do you define again curvature? Curvature in your analysis, we have taken epsilon c by x. If my x value is going to come down, if my denominator is going to have a lesser value, then your strain on the tension steel is going to go up for the same epsilon c, right? And then your curvature is going to increase. So that way, by putting compression steel, you're going to get lesser neutral axis depth for any level of strain analysis. If I'm comparing same section with and without compression steel, by keeping the same amount of tension steel, now I would need lesser x neutral axis depth to satisfy the force equilibrium. So that means that you're going to get more strain on the tension steel, and your curvature is also going to increase. So this is what we have done. If you remember, we have done the analysis for the first case of let's say 1200 mm square, right? So we got when your epsilon c at top becomes 0.0035, if you go back and look at the previous videos, we got x is equal to 51.4 to satisfy force equilibrium. So if I take the curvature for this case for only singly reinforced section, my curvature is going to be 0.0035 divided by 51.4. If you remember the values, we got about 68 point something into 10 to the power of minus 6. Okay, so this is the strain distribution for a singly reinforced section. Now for the same section, now if I put some compression steel, okay, let's say that as ASC, which is equal to 600 mm square. Okay, so if I'm having 600 mm square, to satisfy this, though it is a small amount of steel, you see that my for the same strain at 0.0035, now I need neutral axis depth of 50.83. So now again, curvature epsilon c remains same. Now what has happened to neutral axis depth? So this is for case B, okay, that's what you take. This is for doubly reinforced section. It's for a doubly reinforced section of ASC equal to 600 mm square and AST equal to 1200 mm. So you see that the neutral axis depth is slightly reduced from 51.4 to 50.83. So the curvature is going to increase now. The numerator remains same. Now the denominator is reducing, means curvature is going to increase. Okay. So this is one big advantage by putting compression steel. If you want to maintain or increase ductility without changing your design much, if you put some compression steel, in fact it will help in increasing ductility. Okay, in addition to that, again I said it also helps in fabrication. Okay, the corner bars can be used to hold and anchor the stirrups. Again, stirrups are going to play a major role in columns. It is going to not only help in wrestling shear, it is also going to confine the concrete. But in beams, again, shear resistance is offered by stirrups. We need to hold them properly and anchor them, so that also compression steel helps. Now this is the most important thing, as we said. If your sectional dimensions are kept, if you have a limitation of not changing the sectional dimensions, but if you have to meet the moment resistance demand, you cannot go on put. If you remember in your first analysis for singly reinforced section, if I keep on increasing the tension steel, it doesn't mean that I'll keep on getting higher moment resistance. The moment resistance increase you will get only up to balanced reinforcement ratio, right? For the previous cases, for the constitutive model that what we considered, it worked out to be 3.2 percentage. We can go back, we got about ASC of 7,480 mm square, right? So that was your balance condition. Up to that, you will find that moment resistance kept on increasing. After that, the moment resistance was not increasing much. There was a minor increase, but it was not in proportion to the amount of steel. But if you want higher moment resistance, then you cannot put more steel on the tension side other than row bar. Then what we have to do is we can change. Then the failure mode will become compression control. Steel will not yield when the concrete reaches a failure strain of 0.0035, which is a very brittle mode of failure in beam. We don't want that. We always want steel to reach yielding before concrete reaches its failure strain of 0.0035, right? So what by putting compression steel, then what we can do is, let's say you get a row balanced was 3.2 percentage, but I want to increase the moment resistance. Again, for a particular section, for a row ball, moment resistance also going to be there. But you want higher moment resistance. So how do you do? I can go ahead and put higher row of even 5 percentage. Okay. But what I have to do is this row minus row ball should be put as a compression steel, which is a row prime. Okay. If you do that, then what you have done is artificially you have increased your row ball. Okay. In other words, if the difference, if I'm able to put row bar, then I can keep on increasing my tension steel and I'll get more moment resistance to meet my demand. Okay, so this is the effect. So when you put compression steel, your effective reinforcement ratio at the tension becomes rho minus rho prime. So this is the value. Now it has to be less than rho balanced. Okay. So previously, if I'm putting, let's say, 5 percentage, then what is the rho prime that I need to put? It is going to be 5 minus 3.2, 1.82 percentage of steel that I put it on the compression side. Then I can go up to 5 percentage on the tension steel. Okay, tension side. So this helps in allowing the tension steel to yield before concrete crushes, or I can put more steel, still I can retain the under reinforced failure mode. Okay, now let us see from an example what happens. Okay, so again, this is the same beam, simply supported beam, which is subjected to uniformly distributed load and a point load. Now, in this case, again, we are not considering the effect of axial compression, because here we are talking only about what is the effect of your compression steel. Okay, right? So the bending moment diagram is going to remain same. It's purely from statics. You can derive the bending moment diagram. Now, again, when you look at your free body diagram of your left portion, now this section is also not only having tension steel, it is also having compression steel. So here, what are the forces that are going to act? Of course, P is equal to 0, no axial compression. Okay, no axial compression in this case. Okay, now you'll have CC, that is your concrete. Okay, this is your CC. Now, what is CS? CS is nothing but your compression offered by compression steel. Okay, compression force offered by compression steel. Now, if you look at this equilibrium diagram, again, if you have to draw the forces as, let's say, left to right as positive, or right to left as negative, then what is your force equilibrium? This is your TS, tension force. So TS, if I'm taking that as positive, TS minus CC minus CS should be equal to 0, or in other words, TS should be equal to CC plus CS. Now you see here, when you are no compression steel, when you don't have no compression steel, when P is equal to 0, your equilibrium condition, horizontal force equilibrium, only TS equal to CC when your rho prime was 0 or your compression steel was not there. Okay, compression steel was 0. Okay, so in this case, TS. So now that I have compression steel, that is going to help concrete in offering compression force resistance. So your equilibrium condition is going to be TS will be equal to CC plus CS. Now again, how do we do the analysis? For assumed strain distribution, I can get my stress as a function of a strain in the steel. Stress multiplied by area will give me this force. Now what is CS? For CS, see, steel is good both in compression and tension. Only concrete is very strong in compression but weak in tension. We ignore the contribution of concrete in tension. However, steel is effectively good in compression and tension, provided the steel has to be restrained from undergoing buckling. But anyway, steel is now here surrounded by concrete, so steel in compression is not going to undergo compression in a beam. Okay, so I can calculate my stress in the compression steel. Now, once I know epsilon C at the top fiber and X from your linear strain variations, if I know the location of your compression steel, I can get my epsilon CS. Then once I know epsilon CS from your constitutive equation, I can get my stress. Stress multiplied by area will give me compression force CS, right? Then concrete contribution, anyway, it is alpha F prime C beta X times B. Okay, this is what it is. Now let's run through an example. Now in this case, if you look at it, I am considering the same section that we have done in the first part of the module, where I'm taking a tension steel of 1200 mm square and a compression steel of half the value of your tension steel, which is 1200 mm square, which is 600 mm square. So this is 600 and this is 1200. This is the area of steel that we are looking at. Okay. Now again, for this section, I want to do moment curvature analysis to see what is the effect of putting this compression steel, right? Again, we are keeping exactly same. F prime C is 40. And again, what is F prime C? It is the cylinder strength of concrete. Okay, cylinder compressive strength of concrete, which is different from that of your cube strength and your characteristics. So the next part of the module, we are going to talk about how the IS code design stress strain curves can be used to do the calculation. So that we will do it in the next part. But in this part, we are using the actual stress strain curve. When you test a cylinder in the lab for a 40 megapascal, you will get a parabolic close to the parabolic model. That is what we are going to use, and we are trying to do the calculations, right? Right. So if you do that again, here I am doing just to showing one values of epsilon c equal to 0.0035 only. Okay, because you know the process, and we are just illustrating what is happening for a strain level of 0.0035 in compression at the top fiber of concrete. For this, I'm taking x is equal to 50.83. Let's see from strain distributions again, we can get this. Now, what is this distance? Again, we know that. Okay, what is this distance? It's going to be d minus x, and this is your x. Okay, so again, this cover also we'll know what is the level at which we are putting compression steel. Also, we know generally we call that as d prime, small d prime. Okay, which is an effective cover for your compression steel. Okay, right. So from the similar triangle, we can get the strain of 0.0344. Now again, if you look at it, this is much higher than your yield strain of 0.0025. So the steel has actually yielded. Okay. So what is the tension force? So that means my Fs in the steel is 500 megapascal, right? So the tension force from the steel is 500 multiplied by area, which is 1200 mm square. We divide by the 1000, so you get tension force 6600 kilonewton. Now, again, I need to find what is the level of strain on the compression steel. Now, how do we get that? So, from your similar triangle, what is this distance from here to here? It is nothing but your x minus d prime. So, we can write that as 0.0035 by x should be equal to epsilon cs divided by what is the distance from the neutral axis? It's going to be basically x minus d prime. Per d prime we are taking it as 50 mm, which is the effective curve. So when you plug in these numbers, you get a very small strain. That strain is very small because the reason is the section is heavily under reinforced. Your neutral axis depth is very small at ultimate 50.8, and effective cover is also 50. That is the reason your strain in the compression steel is a very low value of 0.00006. It's almost negligible, but it is giving me slight a strain in compression, so that is going to help. But when you are going for a over reinforced section, we will find that the strain in the compression steel, in fact, the compression steel also can yield. Okay, so you in fact, in a doubly reinforced section, you can have multiple cases. Only tension steel yields. Now you'll have both tension and compression steel yields, or both doesn't yield, right? So multiple cases are possible. But in this case, my compression steel is still elastic, and it is offering a very low strain of 0.0006, which is less than. So compression force can be calculated by stress. Stress is nothing but stress in the compression steel now is strain in the compression steel epsilon cs. Okay, and multiplied by elastic modulus. Okay, so that's what we are doing here. And so it's, and then area of steel is 600. The 600 is basically nothing but your this. Okay, what you have done is 600 here, 1200. So if you substitute, you get a very small force of 7.2 kilonewton. So it's not much. But again, when you look at this, so you get tension force is this, compression force is this, and then for I have to calculate what is the concrete force in compression. So that is again given by alpha f prime c beta 1 x multiplied by breadth of the section. We get about 592.9 kilonewton. Now, what is the equilibrium condition? Again, so you see here, my CC is acting this. Sorry, I should put CC acting this, and then you have CS acting like this, and then you have TS acting like this. Okay, so now I can take moment about any of these points. Okay, usually we take moment about TS. So what is that it is doing? If I'm taking moment about the tension steel, now what would be the moment contribution? So CC multiplied by the lever arm. What is the lever arm is going to be? D minus beta 1 x by 2, that is your lever arm, plus CS. Now CS, what is the distance between CS and this tension most steel? It is going to be effective depth minus what is the cover that you have. Both of them are now in the counterclockwise direction, so that is going to be moment resistance. So M will be equal to CC times D minus beta 1 x by 2 plus CS times d minus d prime by 2. So let us see now what is the force. So again, we are satisfying the compression force is 600 kilonewton, which is equal to a tension force. So we satisfy the force equilibrium. Now we look at the moment, and these are the forces that are acting, which is CC is 592.9 and CS is 7.2 kilonewton, right? It is in compression, so it is acting from right to left. Tension force, which is acting left to right. This is the convention that we have taken. So, okay, so when you take the moment about, see, about the tension state, so we take moment about this point, okay? So when you take moment about this point, this is going to act like this. This is also going to act like this according to their position, right? And these are their lever arm, like we have discussed previously. Okay. So once you plug in these values, you get a moment resistance of about 316.1 kilonewton meter. In fact, this is not, it's exactly similar capacity what we got for your singly reinforced section also with only 1200 mm square. So by putting compression steel of 600 mm square, the moment capacity, you see that it has not really increased much. Now let us look at what is happening to curvature. Curvature also. Now what is curvature again? This is your rotation. So curvature is epsilon c by x. So you put epsilon c 0.0035, x is equal to 50.83. So you get a curvature of about 68.85. Previously you got 68, now you got close to 69. So small increase in your curvature you got. Okay. So if you summarize this calculations for different values of epsilon c, this is for your doubly reinforced section. Okay, this is doubly reinforced. I have compression steel. Of course, I am putting a very small steel, and this is your singly reinforced section. Singly reinforced section. So you see here, the moment capacity when concrete reaches a strain of 0.0035 is 316 here. Here also 316. Absolutely, there is no change. So by adding compression steel to a heavily under reinforced section, why is that we are calling that as an under reinforced section? What is the percentage of tension steel that we have put? Rho is actually 0.5 percentage, 0.5 percent, and rho balance was, if you remember, we got about 3.2 percentage. So rho is much lower than your balanced condition. So it is a heavily under reinforced section. Okay. So steel is going to yield like anything. That is why you got a very high curvature. So for a heavily under reinforced section, if you put the steel, a very small amount of compression steel, is not really helping in increasing your moment capacity, because the failure is still governed by steel yielding in tension. So when steel is yielding in tension, if you don't put more steel on the tension side, if you are putting compression steel, it is not going to give, because the weak link of failure is through steel yielding in tension. So if you do some addition to compression side, it is not really going to do much, except you are going to get some other additional benefits like increase in your ductility, right? So now let's look at this solution. So when you plot this, this is what we got your moment curvature behavior for doubly reinforced section. Okay. And when you plot the same thing for singly reinforced section, almost the curves are overlapping. So only change is the slight change, okay, of curvature. So 68 has become 69. Very small change, because again amount of steel that what we have put is less. So we can, and similarly if you plot this moment and curvature, the moment is, I'm plotting it in the red color. So you see here, absolutely there is no change. If I start in the x-axis, what I am doing is the percentage of ratio of compression steel to tension steel. Okay. So for a heavily under reinforced section, even if I put same amount of tension steel, okay, or in other words, even when ASC becomes in this section becomes 1200 and AST becomes 1200, okay, you are going to get no change. The moment resistance is still is going to be 316 kilonewton meter. Now let us see what happens to curvature. Curvature we are plotting in the secondary axis here. So you see here, curvature also, it is expected to have a slight increase, but it's not really increasing much. Okay, slight improvement will be there. If I zoom the scale and if I look at it, the curvature is going to be slightly higher. Okay, so by putting compression steel, you will get slight increase in curvature, but the moment resistance is not really going to change. Okay, so what we can conclude here is, for an under reinforced section, when you have a row, which is very, very less than your row balanced, your increase in your compression steel, there is no change in moment capacity or curvature. Curvature, there will be small increase. Okay, that's what we've seen.